Welcome to today's virtual seminar, Lysimetry Basics, presented by Leo Rivera.
Welcome to Lysimetry Basics, peering into the black box. I'm Leo Rivera. First off, really to understand why we want to learn about lysimetry and the different technology out there, it's important to understand the motivation behind lysimetry. Water, being one of our most important natural resources, is becoming more scarce, and we're running into issues nowadays where we're having higher rates of groundwater being contaminated as well as surface water being contaminated. And being that water is such an important resource to mankind, especially safe drinking water, it's really important that we understand where the water is going and what's going along with it. And it's really crucial that we understand the water balance and be able to do that. And here you see an equation for the water balance. And two of the values that we use lysimeters to understand are evapotranspiration and drainage. Along with that, it's really important that you understand the solute balance. And a well-known water balance is the basis for any good solute transport investigation. Why do we care about soil water? And why do we want to sample soil water? Well, one, it's important to measure solute concentrations in soil solution. It's important for plant nutrition studies, it's important for ecotoxicology, and it's important for understanding plume assessment, especially when we're trying to protect our groundwater and we're trying to understand proper nutrient application rates for crops and those types of things. It is also important to understand soil water drainage. One, we need to have a good understanding of the water balance that relates to understanding aquifer recharge rates. Especially as many aquifers are becoming more and more depleted, we need to understand where these aquifers are being recharged from and how much water they're receiving. Another application is landfill cover efficacy. In many landfills nowadays, it's important that little to no drainage is moving through these landfills. So, whereas with aquifer recharge, we're trying to measure how much water is moving through the soil, with landfill cover efficacy, we're trying to make sure that there isn't any water moving past the landfill cover into the landfill, potentially leading to groundwater contamination, those types of issues. In wastewater disposal sites, it's important to understand how much water is moving through these areas along with what's coming with it, especially if they want to meet regulatory compliance. And other applications also include contaminant flux. And again, and when you bring these two together, when we understand drainage and solute concentration, it gives us a good understanding of solute flux. It's important in nutrient leaching studies and agricultural operations, especially as areas of the U.S. have more and more groundwaters levels with high levels of nitrates, which lead to health issues for humans, methemoglobinemia in babies, those types of issues. It's also important to understand pesticide fate and contaminant or pathogen transport is just as important, especially in these areas where we're applying wastewater or in areas where we're running into issues with E. coli being transported into either surface water or groundwater. Waste containment, aquifer recharge and contamination. It's important that we have good measurements of all these types of things, especially for areas where it's important that you stay within regulatory compliance. So here's a brief outline of the rest of the presentation. We're first going to go into the history of lysimetry, then go over some different drainage measurement methods, go over the pros and cons of each measurement method. We will then go into some practical considerations, especially on site selection, installation, and how important it is you understand your spatial variability of your site. So, just a few notes on the history of lysimeters. One of the earliest known users of lysimeters to understand percolation of water through the soil was Filippo de la Hire. Filippo de la Hire was a mathematician and meteorologist for King Louis XIV. In 1688, he built one of the first known lysimeters to understand the origin of springs. And really interesting, at the time, a lot of scientists believed that springs were entirely unrelated to rainfall, and they actually thought that springs were recharged from condensation of moist air or ocean water in large crevices in the earth. And Filippo de la Hire was one of the other scientists that believed that percolation of water through the soil from rain or snowmelt was also a big source of groundwater springs, and he wanted to understand that. So he built 3 leaden cylindrical lysimeters at different lengths to measure the percolation of water through the soil and try and get a better understanding of the amount or the contribution of rainfall and snowmelt to water flowing in rivers and streams in France. And the conclusions from this study were still not enough at the time to convince many of the scientists that rainfall was a major contribution to groundwater recharge or the underground springs. In 1875, a botanist and agronomist from Massachusetts, his name was Edward Louis Sturtevant, built one of the first known lysimeters in the U.S. on his farm. An interesting fact about this was, whereas with Filippo de la Hire, his lysimeters were small cylinders, and they were repacked cylinders, Edward Louis Sturtevant built what they called at the time a soil block lysimeter, which was essentially a large intact monolith, which at the time, you could imagine, was quite the undertaking and a lot of work to build a lysimeter like that. Then the first weighing lysimeter was built in 1937 in Coshocton, Ohio, and this was built by the then Soil Conservation Services, now known as the NRCS, and this was one of the first known weighing lysimeters, and they used this to understand evapotranspiration rates of crops. And one interesting thing about this was they showed that they were able to show the influence that dew formation and different crops had on the water balance. So now let's go into some different drainage measurement methods. We'll start with the most basic measurement methods and go into the more complex methods. So one of the first methods, and this is actually not a direct measurement of deep drainage, is the water balance residual. And essentially the water balance residual, you're measuring every component of the water balance: precipitation, irrigation, runoff, storage, and evapotranspiration. And then by doing this, you're back calculating drainage. This is a really complex method because there's so many measurements that you have to take and you have to make them accurately. And that can lead into errors if you have any small errors in those measurements. That can result in a large error in the deep drainage measurement, the drainage measurement. And here's a couple of examples of this. So say we're taking a measurement of the water balance residual in an area with 150 centimeters of precipitation and good vegetative cover. If we're able to make a 10% or a measurement with only 10% error in evapotranspiration, which is not an easy measurement to do, and giving 10% error is a very good measurement, this will result in a 17% error in drainage. So given that's not bad, it's a good drainage measurement value, it works out well for this area. But then we go into situations, say we have a 20 centimeters of annual precipitation, and we again have a 10% error in the evapotranspiration measurement. that results in a 300% error in drainage, which is just unacceptable and would not work well for this area. Now, one nice thing about the water balance residual, as compared to a lot of the other measurement methods, is you're actually taking a measurement of the large area. So you get a large scale measurement of deep drainage and the entire water balance. So it works very well when you're trying to understand field scale, water movement, and the water balance at field scale. Another issue with the water balance residual is you do not have a measurement of soil water solute concentration. So you don't get any measurements of solute flux. Now, if this is something that's important to you, you can add pore water samplers, also known as suction lysimeters, to get at the solute concentration, and then you can calculate solute flux based on the measurement of the water balance residual. So our next method is, again, another very basic measurement of drainage, is the zero tension pan lysimeter. With the zero tension pan lysimeter, you essentially start installing a large box or a large open chamber underneath the soil, or repacked soil over it, with a drainage grate allowing the water to freely drain into the pan. Now, there are many issues with the zero tension pan lysimeter. One of the most basic issues is pure soil physics. Water flows from low tension to high tension, or high potential to low potential. So because you're installing a pan lysimeter that is at zero tension into soil that has water held under tension, the water is just naturally not going to want to flow into the lysimeter. So water in unsaturated soil will flow around the lysimeter, or what we call flow divergence, resulting in high errors in your drainage measurement, and just not a good understanding of the water balance. Really, the only time you get a representative sample is under saturated conditions. So here's an example. Here's just an illustration of this. You have a pan lysimeter at zero tension, or 0 kilopascals. Say you have the water in the soil being held at 40 kilopascals. The water is just going to flow around the lysimeter towards areas of higher tension. Now, say we were able to match that tension, then we could get a more representative measurement of the deep drainage value. And that'll lead us into our next drainage measurement method. So, again, there are problems with the zero tension pan lysimeters, but one of the advantages of them is they're cheap, and you can kind of mitigate some of these problems. One, by making a large measurement footprint. You can see a picture on the left here of very large pan lysimeters. That will help mitigate a lot of the divergence problems. Another method is installing large vertical walls, where you're essentially trapping the water in the soil and forcing it to have to go through the lysimeter. Now, yes, this will help improve the collection efficiencies, but what it does is it changes the water holding capacity of the soil because of that zero tension lower boundary. So again, it's still not going to be an efficient measurement. And even with all of these methods for mitigating these problems, it's very common to still see collection efficiencies of less than 10%. So that leads us into our next measurement method, static tension lysimeter. With a static tension lysimeter, we either use a vacuum pump or a wick to create a static tension. And by doing this, we're trying to match the tension that the water is held within the soil, or at least give an optimal tension to really improve the collection efficiency of the sampler and reduce the issues of divergence. Now, by doing this, that does result where there is the possibility for flow convergence, where because we're applying too much of a tension, for example, the water in the soil is being held at only 5 kilopascals, very close to saturation, that will, and our tension being applied by our suction lysimeter, or our static tension lysimeter, sorry, is higher than that, say 15 to 20 kilopascals, we get an overestimation of the drainage value. So there are some methods to counteract this, and we'll get into that here in a second. But one of the more common static tension lysimeters is a Wick Lysimeter. And essentially what you're doing with a Wick Lysimeter is we're using a wick to create a hanging water column, and that is used to pull tension on the soil water. And we try and choose a static tension that will optimize the water collection efficiency. And you can kind of see a breakdown of what a Wick Lysimeter would look like. We would have, for example, a 60 centimeter wick in contact with the soil, pulling the water into a sampling reservoir. Another tool for these Wick lysimeters, or the passive capillary lysimeter, is to add a divergence control tube to minimize the divergence and convergence, because again we're installing large walls, trapping the water within the soil column, as well as extending the tension from the wick up through the soil. And this has been found to really help improve the collection efficiency and reduce the amount of divergence and convergence. And there was some work done by Glendon Gee over at the Pacific Northwest National Laboratory using these to try and find an optimal height for a divergence control tube. And so what we see here is a graph of the collection efficiencies in a sand. And what you find is once you get past about 25 centimeters, we start getting 100% collection efficiency in a sandy soil. And that's great. So if you were to install a 60 centimeter divergence control tube in a sandy soil, you're going to be able to get 100% collection efficiency across many different drainage values, ranging from 1 millimeter per year to 10,000 millimeters per year. In a silt-loam soil, however, we start to lose that collection efficiency, especially in the very low drainage values. In the really the only time that we get a good collection efficiency is at 10,000 millimeters per year, and with the 60 centimeter divergence control tube, we get about 80% collection efficiency. We could go higher up to 100 centimeters, but we still don't quite reach 100% collection efficiency. And then in a clay soil, very similar. For some reason, it worked a little bit better in the clay soil. It's probably just dealing with the way the soil holds onto water, the moisture release curve, those types of things. But you can see with a 60 centimeter divergence control tube, we're getting above 70% collection efficiency at 1,000 millimeters per year and 10,000 millimeters per year drainage rates. So, we'll go back. So you can see that some of the issues with the static tension lysimeters is that it's not going to work well in all soil types. It's going to be more of an optimal tool for coarser textured soils, or if you're working in a finer textured soil with higher drainage rates. So something to consider when you're thinking about different methods for collecting drainage measurements. Now our next tool is a controlled tension lysimeter. You're going to have very similar construction to either a pan lysimeter or even a static tension lysimeter, but instead of being static, we're constantly changing the tension in the soil, in the lysimeter, to match the tension in the soil. The tension in the lysimeter is actively controlled based on soil water tension measurements, either using a tensiometer or some other type of matrix potential sensor. And then we use a control system to read the tensiometer and vacuum gauge and control the vacuum pump. Now in the past, this used to be a more complex method, and setting something up like this was not easy. It took a lot of programming skills with different loggers and control algorithms, that type of stuff. And And so here you can see an example of a controlled tension lysimeter. We have two suction plates at two different spots in the soil, and a tensiometer measuring the matrix potential at the same point in the soil, and we're controlling the tension on these lysimeters based on the matrix potential measurement from the tensiometer. But nowadays, there are new tools, more turnkey systems to make this easier. Now, one of the advantages of the controlled tension lysimeter is it's going to give you the most accurate drainage measurement method across all soil types and drainage rates. It's going to give you the most accurate measurement method. The drawback to this system is it is going to be expensive. It's going to be a little more complex, even with the turnkey systems, and it's going to be power intensive and a little more maintenance intensive than your static tension lysimeters or your pan lysimeters. That then moves us into the next method, which is the weighing lysimeters. Now, the weighing lysimeters have a lot of advantages over all the other measurements. You get a large surface area. They're also deep enough to encompass the root zone. And the way they work is they use precision load cells to measure the lysimeter continuously. And then the lower boundary is controlled with active suction, just like with a controlled tension lysimeter. So by combining these two measurements, the active suction being controlled with at the lower boundary and the weight measurement, it gives us the deep drainage measurement along with the total water storage, allowing us to calculate evapotranspiration. Whereas with the other types of lysimeters, the static tension lysimeters, the pan lysimeters, and the controlled tension lysimeters, we only get a drainage measurement method. So with the weighing lysimeters, we get both drainage and we're able to calculate evapotranspiration based on weight change within the lysimeter, which is a really nice ability, and it really helps us in understanding evapotranspiration rates of crops and really understanding the water balance in an area. So the way a weighing lysimeter would be constructed is you would first take an intact monolith, similar to the ones that you see here. We would then install them in a variety of configurations. You can install them in a large facility, like what you see in this bottom right-hand corner. You could install them in a smaller cluster, like what you see in the top right-hand corner. Or you could have individual lysimeters out within the area. Here on the left, you see a large lysimeter research facility out at the Helmholtz Research Center outside of Munich. And with these large research facilities with the lysimeters, they're really nice for being able to control everything within the lysimeter, and really nice to be able to maintain these lysimeters within these large research facilities. If you see within this, in the picture in the bottom right-hand corner, if they ever need to make any sensor replacement within the lysimeter or do any maintenance to the lysimeter, it's very simple for them to just lower the lysimeter into the facility and change the sensor out or do any maintenance, and then push it right back up into its cavity. Now, there have been some issues with these types of large facilities, especially when it comes to temperature dynamics, and we'll talk about that here in a little bit. Now, when using a large weighing lysimeter or these large-scale weighing lysimeters, it's really important that you're able to match the field water dynamics within the lysimeter. And in the past, we could actively control the suction, which allowed us to control the intake rates and the drainage rates within the lysimeter, actively controlling that with the reference tensiometer, giving us a good accurate value of deep drainage. Now, what happens sometimes is when you have soil drying down and you actually have water moving through the soil due to capillary rise, the soil in the lysimeter can actually dry out faster than what it is in the actual soil, because there's no water being pumped back through. So what we do now then is we use a bidirectional pump, and this pump allows us to actually pump water back into the lysimeter, actively matching what's going on within the native soil, giving us an accurate value of, or accurate understanding of evapotranspiration rates throughout the entire soil and not just within the lysimeter. So it's really nice functionality. And then we move into understanding the field temperature dynamics. Like I said before, with these large facilities, that was an issue, is the lysimeters, the temperature dynamics through these lysimeters did not match what was happening in the field. And it's because you have them installed in this large room with, where you can have large temperature gradients due to opening the door of the facility, or you're just maintaining that soil at a certain temperature within the facility that just does not match what's happening in the field. So instead, a way to counteract this is to use wells that are made out of porous concrete. And what this does is it allows for water vapor to move through the porous concrete, and by doing this we create kind of an evaporation enthalpy within the well, matching the temperatures of the lysimeter throughout the entire lysimeter with the temperature dynamics in the native soil. And you can kind of see some graphs of that here. We have 4 different temperature measurements, or 8 temperature measurements made at 4 different depths, one within the lysimeter and another within the native soil. And you can see that with this type of method, at all 4 depths, the temperature gradients in the lysimeter are matching the temperature gradients within the native soil within 1 to 2 degrees Celsius. A nice thing about weighing lysimeters is they give us the best possible quantification of the hydrologic cycle. It's really important for understanding climate change. There is a large research project going on in Germany called the Torino Soil Can, and what they're doing there is taking monoliths from the northern climates and the colder climates in Germany and moving them down to the warmer climates, and vice versa, moving the lysimeters from warmer climates and moving them to colder climates to help give them an understanding of what would happen during as climate change in certain areas, as far as solute transport, the nutrient cycle, those types of things. So that's a really interesting project where they're using weighing lysimeters to help understand climate change. It's a great tool for ecohydrology and for understanding contaminant transport, because you can use these to quantify the hydrologic cycle along with putting samplers within different points in the lysimeter and really get an understanding at how contaminants are changing as they move through the soil and at what rate they're moving through the soil. Now, the drawbacks to these large weighing lysimeters are, as you can see, especially in those large facilities, they're going to be very installation intensive. It's a lot of large machinery. It's going to take a lot of work. They're not easy to install. They're also more maintenance intensive, and they're going to be more expensive than any of the other drainage measurement methods. The costs of these have gone down as compared to what they used to be 10 years ago, but they are still expensive compared to other lysimeters or other drainage measurement methods. That then moves us into the small-scale weighing lysimeters. And what we have with the small-scale weighing lysimeters is the same technology, but scaled down. And really the nice thing about these small-scale weighing lysimeters is that they're easier to install, and you can get the same measurement, of course, on a smaller scale, at a much lower cost than the larger weighing lysimeters. And you can see some images of the smaller scale weighing lysimeters here. The installation can be done by hand instead of having to use large equipment. It's much easier to do, and and you use the, just like with the large lysimeters, you use a precision load cell to weigh the monolith, and you're actively controlling the suction at the bottom of the lysimeter to really allowing you to get that same accurate measurement that you get with the large lysimeters with these smaller lysimeters at a lower cost. Again, some disadvantages to this is it is a smaller footprint. But if you're trying to understand these measurements at this small scale, they're really a great tool for this. So now we'll move into some practical considerations. There are many considerations that you need to think about when you're wanting to install lysimeters and trying to take these measurements. One, it's important that you get representative soil of what you're trying to measure. If you're going to take a large monolith and you're trying to understand large scale processes within a smaller lysimeter, it's important that you select representative soil of the entire site. And this can be hard, especially in areas where you have a lot of spatial variability. But it's important that you understand your site and you take these into consideration. It's also important that you have soil that is deep enough to install the lysimeter. If you have soil with shallow bedrock or just large gravel or cobbles shallow within the soil, a lysimeter might not be a very good tool on these sites, or at least not a tall lysimeter. You could go with a shorter 30 centimeter lysimeter and try to get an understanding there, or you can go with a repacked lysimeter, possibly in these areas. But these are things that you have to think about. And also, you need to determine whether you want to take an intact monolith or you want to do a repacked core. And again, it's really based on what your research project is and what you're trying to understand. And with the installation, undisturbed soil is always preferable. It's just so crucial that you have soil structure within the monolith that matches what you're trying to measure, because structure is one of the most important factors in water flow and solute transport and these dynamics. So if you destroy the structure, you're going to change things, and so it's important that you keep that take that into consideration. It's possible to take an intact monolith with wick and weighing lysimeters, or if you're trying to get underneath the native structure using something like a pan or a controlled tension lysimeter, what you can do is dig out a pit and do a horizontal insertion of the pan or the controlled tension lysimeter underneath the native soil, and then press it up and put it in contact with the native soil. So these are things to think about when you're thinking about installing a monolith. Another important factor when looking at this is making sure that the soil that you are trying to install in or take a monolith of is at optimal soil moisture. If you try and take a monolith or do installations while the soil is too dry, you're going to run into issues like this where you see in this picture where it starts breaking or you can't get a good monolith. So it's just, it's really important that you do select the right time to do your installation. It's also important that you have good hydraulic contact with the soil column. If you're using a pan lysimeter, it's important that you, or a controlled tension lysimeter, it's important that you're able to press the lysimeter up into contact with the native soil, or if you're doing a horizontal installation. A good thing to do here is use diatomaceous earth or silica flour in between the soil and the lysimeter to help ensure good hydraulic contact. It's also important that you get it below the root zone. If you don't get your lysimeter installed below the root zone, one of the issues you're going to run into is you're going to start measuring water as deep drainage that actually could be used by the plants and transpired or be lost through evaporation. So it's important that you get below the root zone. And it's also important that the vegetation above your lysimeter is representative of what you're trying to measure. So all these things are just very important to consider. It's also, if you're doing an installation with, say, a controlled static tension lysimeter, where you're actually having to dig out below the soil, it's important to try and maintain the vegetation above it for faster recovery, and that way, with your measurement, you start getting more representative values earlier on within your study. And one last thing that's really important to understand is spatial variability of soil. This is oftentimes one thing that a lot of people don't take into consideration, but soil is incredibly spatially variable, especially in, just within certain areas, especially when you have varying topography. There's going to be spatial variability of vegetation, so it's important that these things are considered. And one other thing to consider, and this is especially an issue in areas with high clay content soils, is macropore flow. In areas like Texas, in the Blackland Prairie, you run into these high shrink swell soils of vertisols that form large cracks, like you see in this this middle picture here. And these large cracks lead to high amounts of macropore flow and preferential flow that you won't see in other areas. And so it's important that if you're working in an area like this, that you either have a large area to encompass these preferential flow paths, or that you have multiple measurement sites to help capture this spatial variability. That's incredibly crucial in these areas. Clay soils are just a tough soil to make any type of measurement in. Either let it be soil moisture measurements, deep drainage measurements, any of these measurements. I often like to say that clay soil is the vein of my existence. But it's there, and we have to try and understand it, and so it's important that these things are considered. So here's just a little breakdown of all these methods that we just went over. With the soil water sampling, with the water balance residual, we do get a measurement of drainage. We don't get a measurement of solute flux or solute concentration unless we use soil water samplers to go along with it. Accuracy can be poor. A nice thing about the water balance residual, is you do get field scale measurements, and at a much larger scale than you do with any of the other measurement methods. They are installation and maintenance intensive. If you've ever had to set up eddy covariance towers or eddy flux towers or anything along those lines, you'll understand what I'm talking about. And they are a little bit higher in cost. And again, it's an indirect estimate or measurement of deep drainage, whereas with the other measurements, you get a direct measurement of deep drainage. With the pan lysimeter, you get both solute concentration, deep drainage, and solute flux. You have poor accuracy. You can get medium to large spatial scale measurements. It's going to be a little more. It's going to be installation intensive, just like any of the other lysimeters, but it's going to be low maintenance in the long run, and it's probably the cheapest method of all the deep drainage measurement methods. But again, the issue with these is flux divergence, especially in unsaturated conditions. And with the static tension lysimeter or a Wick Lysimeter, you get the same. You get solute concentration measurements, drainage measurement methods, and solute flux measurement methods. You get fair accuracy over the pan lysimeter. And with these, you get a more smaller to medium scale measurement depending on how large your lysimeter is. It's going to be about the same installation as required with the pan lysimeter. A little more expensive, but you get mid-range accuracy with mid-range cost. And then with control tension lysimeters, you get the same measurements as you get with the pan lysimeter and the static tension lysimeter. You get excellent accuracy. It's the best measurement method for trying to quantify deep drainage. You get medium scale, depending on how big the suction plate you go with. It's about the same installation requirement as a pan or static tension lysimeter, but it is going to be more maintenance intensive, and it's going to be more expensive. But again, the nice thing about these is there's minimal flux divergence or convergence And there are new turnkey systems that make this easier to use and require a little less maintenance, and actually make this a little less expensive than what it used to be. And then with weighing lysimeters, you get, again, solute concentration measurements, drainage measurement methods, and the solute flux measurement method. This is going to give you the best accuracy of both deep drainage and evapotranspiration. And you're going to get medium scale, again, depending on how large of a weighing lysimeter you go with. But this is going to require a lot more maintenance, and it's going to be, the installation with these is going to be much more intensive than any of the other measurement methods. And it's also going to be a much more expensive method. But the great thing about weighing lysimeters is it allows you the ability to quantify and manipulate the hydrology if you want to manipulate it, or just match it with the native soil. And then along with this, there have been the introductions of smaller scale weighing lysimeters that help bring the cost down and bring the installation complexity down a little bit. All right, well, thank you very much.